All right, I know I've been talking about the chain rule for a long time, but I am excited to say that we are finally here. We are finally at the point where we can use this thing that I've been talking about all the time. So we're going to start by introducing it. Now, the chain rule is used when we have function composition. So let's look at this function I have on the top right here, this blue graph. This is the sine of x squared plus 1. This is a function of a function, f of g, if you remember that from pre-calculus. So the outside function is sine, and the inside function is x squared plus 1. So there's a couple of ways of guessing what the derivative might be. So let's go through some natural guesses. So you might think, well, let's just try to take the derivative of both. So the derivative of sine is cosine, and the derivative of the inside is 2x. And let's see, is this the derivative? Well, right off the bat, look at minimums and maximums. That's the easiest place to verify whether something's a derivative. Right, the minimum of this blue graph, here, let me zoom out so you can see on the left which one's blue and which one's green. The minimum here, this has a horizontal tangent line. The derivative should be 0 here. But notice that the green graph is not 0 here. The green graph is our guess of the derivative. And the green graph says that we should have a slope of negative 0.779. Green graph is a slope graph, derivative graph. It tells us the slope of the blue graph. So this can't be the derivative. Well, maybe we just take the derivative of the outside and leave the inside alone. Again, oh, look at this. This does have a 0 function value right here. Okay, this is looking positive. This is looking good. Has a 0 function value here. Okay. Okay. Wait, this actually looks good in a lot of metrics. This isn't supposed to be the right answer. All right, where does this fail? What's the problem here? All right, this has a positive. Green graph is positive right here. Green graph's positive here. That means that the blue graph should have a positive slope. Blue graph has a negative slope, so this can't be right. This is closer though. This it almost scared me for a second. I was like, let's show them why this is wrong. And then I was like, why is this wrong? There's probably a couple more things that you can find. Green is our derivative guess. So positive green should be a positive slope on blue, but it's not. Well, let's get an approximation. For small h, right, the derivative is the limit as h goes to 0. This is just rise over run. Change in the function value divided by the change in the inputs. And as that gets really close, as this is the slope of the secant line between 2 points, and as those 2 points get really close together, as h goes to 0, this should approximate the derivative. So this is when h is 1. This is when h is 0.5, 0.4, 0.3. It's moving a little bit, shifting a little bit. 0.01. Look at that orange graph. And, you know, once h gets small enough, this is basically our derivative. So again, we have the properties that we were talking about before. When the blue graph is at a local minimum, when the blue graph has a horizontal tangent line, the orange graph has a function value of 0. That's great. Again, orange is 0. Orange is 0. Orange is 0. Orange is 0. All of these orange values of 0 correspond to the top or the bottom of little humps or valleys. So the orange graph is indeed the derivative. Let's get rid of the blue graph real quick. And again, let's try to combine these things. And this is the actual answer. Notice that if I multiply our guess, which was close, this green graph, well, actually this green graph doesn't look very close, but it had some of the right aspects. If we multiply the green graph by a 2x, by the derivative of that inside function, then that's the actual derivative here. So what do we do? What do we do? Let's look at the difference between blue and green on the left. The derivative of sine is cosine. The inside stayed the same, but then we had to multiply by the derivative of what whatever was on the inside. Okay, and that is indeed what the chain rule is all about. We're not going to prove the chain rule. It's pretty complicated to prove, but this is kind of just a little intuition and a little exploration and a little connection of different concepts for where it comes from. All right, so here it is, the chain rule. And there's two ways that we're going to be using the chain rule here. We're going to do them side by side. So let h of x be f of g of x. We have function composition here. And there's different ways of writing f of g of x. Remember your pre-calculus. All right, this is just some function inside another function. In our example, f was the outside function. F was sine of x. And g is the inside function. G was x squared plus 1. All right. And h is just f of g, g inside of f. So if this is our h, then, and we're going to make some assumptions. We're going to say, let this function be nice enough. Check the textbook for more details on what nice enough means. But for brevity, I don't want to go into it too much. Then the derivative of h is, well, what did we do? Look at that bottom one. We took the derivative of the outside function sine, derivative of sine is cosine. We took the derivative of the outside function, we left the inside function alone, and then we multiplied by the derivative of that inside function. Well, that's exactly represented like this. Derivative of the outside function, f prime, leave the inside alone, and then multiply by the derivative of the inside function. This is the chain rule. This is how we take the derivative of function composition. Oh, excuse me. And we can also write this in another form. Another form. This is the second form is going to use Leibniz notation, which we don't use that much in this class, but it's good to be aware of. If we let, let's see, what are my variables going to be? If we let y be h of x and u be g of x, then the derivative of y with respect to x, again, if y is h of x, these are the same things. Y is h of x. The derivative of y with respect to x is the derivative of y with respect to u. Again, that's the derivative of the outside function times du dx. Again, u is g of x, so g prime is just du dx. So these really are the same thing. This is dy du, this is du dx. Again, this means what is the derivative of y with respect to the u variable? What is the derivative of u with respect to the x variable? We'll be using both of them. So these are the big ticket items in this section. We're going to do 2 or 3 example problems next, and then the whole next video is just a bunch more example problems. All right, but we're going to start by trying to illustrate a couple different, both of the methods. And there's really kind of a lot of ways to approach these. Find the derivative of the following. H of x equals 1 over 3x squared plus 1 quantity squared. Okay, so first off, this is indeed function composition. We have an inside function, 3x squared plus 1, and an outside function, 1 divided by something squared. So there's a couple of ways of approaching this. Let's do it with 2 methods. Let's use this top method. Top method we'll do in red. The bottom method we'll show that in blue. And we can compare. So now it really depends on how exact and how step-by-step process you want to do it. By the end of this section, I'm hoping that we're going to be able to use a couple of methods and be a little faster, but maybe it'll take a while, and that's okay. But again, let's just show that h of x is indeed f of g of x, and g is our inside function. You may remember doing this exact same thing in pre-calculus. What's the inside function? 3x squared plus 1. What's the outside function? It's 1 over that thing squared. That thing is our variable. And it's 1 divided by it. We're going to use the power rule, so let's write it in this form with a negative exponent. And then again, you should be able to review function composition, pre-calculus, algebra 2 maybe. If we plug g into f, into f, we should indeed get h. So this should indeed be function composition. So the chain rule says that the derivative of h is f prime of g of x times g prime of x. Well, what's f prime? Oh, we should probably have written that down somewhere. F prime of x uses the power rule. F prime of x, bring the power down and subtract 1 from the exponent. And g prime, power rule again, is 6x. Remember, the derivative of a constant is 0. So quick reminder, because they're very closely related. When you're just taking the derivative of a constant, it's 0. But when you're taking the derivative of a constant times something, then it comes out in front. So it's easy to get these confused. One is just a constant, and the other is the constant multiple rule. So watch out for those two, okay? All right, then if we do the chain rule, we take the derivative of the outside function, which is negative 2x to the negative third. But we're evaluating it at the inside function. The inside remains unchanged, 3x squared plus 1. And then we multiply by the derivative of the inside, which is 6x. And we'll simplify. All right. This is the really formal way of doing it. In part B, I'm going to do it a slightly less formal and more common way. So if this formal way kind of trips you up, especially this step might trip you up, don't worry, we're going to be seeing some other ways too. So if we simplify this all out, this should be negative 12x times 3x squared plus 1 cubed. Just using that negative exponent. And this is all you can do here. That is our derivative. But you can also use Leibniz notation, right? Y equals, again, 3x squared plus 1 to the negative second power, where u is the inside function, right? U is the inside function, and y is h. So if u equals the inside function, 3x squared plus 1, y is just u to the negative second. Again, this is really the same thing, just instead of f and g, it's y and u. Okay, notice again, right? These are the exact same thing, just different letters. But I think this one is actually a little bit more easy to see formally why it's the case. So let's copy down Leibniz form for the chain rule. dy dx equals dy du, du dx. And as a side note, these aren't fractions in the traditional sense, but sometimes they kind of work the same way that we think fractions should work, right? If these were actually fractions, you'd cancel and you get dy dx. Now they aren't, but that's an intuitive way to remember. Again, if these were fractions, we'd really be kind of silly because the d's would cancel too, but They're derivatives. It's just using this notation. So what is the derivative of y with respect to u? That's just what the derivative of this is. Use the power rule. -2, u to the -3rd. What's the derivative of u with respect to x? Again, the power rule. It's 6x. And now all that's left is getting everything back in terms of x. So our final step is saying, well, what is u? Plug it back in. It's -2 times u, just 3x squared plus 1, times 6x. And should notice that these are the same things. So that's another way to get to this final answer. Red method, blue method. Let's do one more. Part B. Find the derivative of sine cubed of x. And again, I would recommend as a first step, rewriting this function. Remember sine cubed? That just means sine of x cubed. The top thing is a shorthand that we use a lot, but the bottom thing is what it actually means. And again, we should have a clear viewing of what the inside function is and what the outside function is. So let's use Leibniz notation first. Y is equal to, well, let's start with u. Usually easier to start with the inside function. U is sine of x, so what is y in terms of u? Well, if you just replace sine of x with u, y is just u cubed. Now dy dx is equal to dy du times du dx. We just take each derivative and multiply them together. The derivative of y with respect to u, power rule, it's 3u squared. Derivative of u with respect to x is cosine of x. And all that's left is, replacing u at the end. So it's 3 times u squared, which is sine squared of x, times cosine of x. Oh no! Forgive me. I said blue method was Leibniz notation. Oh no, our color coordination is gone. Wait, watch this. You want to see me fix it? Never mind, that didn't fix it. All right, well, I got nothing. So I'm going to show you, so the red method that I did over here, I can't even say that anymore. This first method I did, 1, 2. This first method that I did over here, we don't usually write it with F's and G's. Usually we do it a little bit more informally. So this is a common thing that you're going to see as well for part B. And again, I do think Leibniz notation is very clean. I really like this second method. But this first method, we also do it a little bit more informally in practice. We take the derivative of the outside function and leave the inside alone. That's what we say. Derivative of the outside function, leave the inside alone. So the derivative, we take the derivative of that cubed and use the power rule. 3, subtract a power, leave the inside alone, and then we multiply by the derivative of the inside function. So that's usually how most people use a chain rule after a lot of practice. And you can see that it does still get to the same answer. I'm not going to write out the step, but again, it does simplify exactly to that. This time I didn't even do it in blue, I did it in white. All right, so a couple of ways of seeing this. We're going to do a little bit of both methods in the next video as well. Let me know if you have any questions and enjoy the chain rule. I'm happy to finally be here.